Hello, my name is Yanan. I'm a graduate student in the Ultrafast Dynamics lab here at the University of Pittsburgh. Our lab has been dedicated in studying the plasmonic and excitonic phenomena using photoemission spectroscopy and microscopy. Recently, we published a perspective in the Journal of Physical Chemistry Letters reviewing the ultrafast microscopic study of surface plasmons.
This research has been supported by the National Science Foundation Center for Chemistry and the Space-Time Limit.
When light illuminates a nanoscale metal asperity, it locally excites subwavelength collective oscillations of conduction band electrons, which are called localized surface plasmons. The unique physical properties of localized surface plasmons, such as subwavelength field confinement and corresponding enhancement, can greatly improve the efficiency of photocatalysis, solar energy conversion, and surface-sensitive spectroscopy. Besides localized mode, the collective electron motions can propagate at metal dielectric interface at the local speed of light in the form of a surface electromagnetic wave that are known as surface plasmon polaritons. Such propagating mode carries transverse spin orthogonal to the direction of propagation, meaning that counterpropagating plasmon waves have opposite spin directions, which is a manifestation of quantum spin Hall effect of light. Therefore, SPPs can be utilized to achieve chiral optical forces technique and spin orbit coupling assisted plasmonic circuits, etc. Most of the plasmon-related physical and chemical phenomena occur on femtosecond timescale, or 10 to the negative 15th second. Therefore, we need an ultrafast microscopy to resolve the plasmon field.
In our lab, we employ an aberration-corrected low-energy electron microscope from Specs in Germany, which also serves as a photoemission electron microscope to study plasmonic phenomena with nanometer spatial and femtosecond temporal resolution.
In the LEAM mode, the reflected electrons from the sample form an image of the surface topography, while in PEAM mode, photoelectrons generated by ultra-short pulses form an image of the surface polarization field. The excitation light pulses are as short as 15 femtosecond, which allows us to observe electron dynamics on the femtosecond timescale. To produce such short light pulses and tune into plasmon resonance, we use a wavelength tunable femtosecond laser system, which works on a non-collinear optical parametric amplifier principle and is pumped by an impulse fiber laser system that is manufactured by Clark MXR. The plasmonic structures that we study are grown in situ by silver atom evaporation onto a clean silicon substrate. For example, in the first movie, we can image how the first 1-atom thick layer of silver atoms grow on silicon surface with 1-1-1 crystalline orientation. The first layer is a wetting film on top of which nucleate into three-dimensional single crystals of silver. The second movie is the nucleation of a silver island, where we observe a crystal terraces flow in space as the island grows. When the island is illuminated by femtosecond pulses, surface plasmon polaritons are excited and launched at its sharp edges. Because nothing is faster than light, we cannot directly take snapshots of light propagating on the silver vacuum interface. Instead, we detect an interference pattern between the surface plasmon polariton and the light that excited it, which forms a static grading pattern of enhanced and depressed fields on the surface. Where the field is enhanced, the absorption of light to excite photoelectrons will be favored, and where the field is depressed, such excitation will be suppressed. By integrating many cycles of excitations of plasmon, PEAM records such static interference patterns which record an image of the plasmonic field. To record that actual surface plasmon polariton motion, we use excitation with identical pulse pairs, which are produced by a Mach-Zehnder interferometer. The interferometer can control and scan the delay between the two pulses with precision of a few tens of attoseconds. With two pulses, we can use the first pulse to excite a surface plasmon polariton and the second delayed pulse to create the interference pattern. This interference pattern then moves in space as we change the time delay between the pump and probe beams because the regions of constructive and destructive interference depend on their relative delay. Therefore, the probe beam can detect the motion of the plasmon field excited by the pump beam. By stacking of the PEAM images acquired sequentially as we advance the pump probe delay, we generate a movie of light propagating as that surface plasmon polaritons on silver vacuum interface. Indeed, our movies show the fastest phenomena ever imaged. It takes light 499 seconds to travel from the Sun to the Earth, but in our microscope, we can capture as it propagates by 300 nanometers in each femtosecond. What we learn from the electron dynamics are the phase and groove velocities of the surface plasma polarities, which determine the ultrafast signal transport in plasmonic circuits, and they are also crucial in the understanding of the charge transfer process of chemical reactions that happen on the nanometer spatial and femtosecond temporal scale.